We've already got an idea about how we can approximate the area of a curved region by replacing that curved region with rectangles. We've already done this. If I want to approximate the area under the curve, I'll just add up the areas of these rectangles. And that's a pretty good approximation if these rectangles are thin enough. If I make those rectangles thinner and thinner, that gives me better and better approximations to the area under the curve. In fact, more than just approximating the area under the curve, by making those rectangles thinner and thinner, I can write down a definition of the area under the curve. This is the setup. I got some function y equals f of x, which I've plotted in orange, and I want to define the area of this region, right? It's the region below the graph, above the x-axis, to the right of the line x equals a, and to the left of the line x equals b. It's this region inside here, and I want to know its area. But what does that even mean, right? Because this region's got this curved top. It makes it very complicated. So I define this area by taking a limit of approximations, right? I get those approximations by cutting this region up into rectangles. And if I make those rectangles thin enough, I get better and better approximations to what I'm hoping to be the real area under the curve, right? So I'll define the area under the curve to be the limit of these approximations as the approximations get better. I'm going to denote that limit like this. It's going to be the integral, this long s, from a to b of f of x dx. Now, why f of x dx? Well, f of x is the height here, and dx is, I'm imagining, a small distance here, a small width. So f of x dx is really a shorthand way of talking about the area of one of these rectangles, and then this long s is for summing all of these rectangles, right? It's adding up these rectangles, these thin rectangles, in order to define the area under the curve. Here is the precise definition of the integral. Precisely, the integral of this function from a to b is a limit over partitions of the Riemann sum, right? And it's a limit over partitions where I've also chosen some sample points for those partitions. And I'm taking the limit as the maximum width of a subinterval in that partition goes to 0. In order to ensure that all of the widths of the subintervals are going to 0, I just demand that the maximum one, the biggest one, goes to 0, and that forces all the other ones to be small as well. I have to say that the maximum width goes to 0 to prevent some sort of bizarre scenario where I've got one really big subinterval and then lots and lots of small subintervals, right? I want to make sure that all of those subintervals are getting very narrow so that I'm getting a very fine partition in the limit. There's no guarantee whatsoever that that limit actually exists. On the other hand, here's a theorem. If a function f is continuous, then it's integrable, meaning that the integral, right, the integral of the function from, say, a to b actually exists. So when I say integrable, what do I even mean by integrable? If I were to claim that the integral of f from a to b is equal to some number big I, what that means is that no matter how I partition the interval from a to b, as long as that partition is fine enough, right, as long as the maximum width of any rectangle in my skyscraper picture is small enough, right, as long as the widest one is thin enough, then no matter how I choose those sample points within each of the subintervals in my partition, the resulting Riemann sum that I calculate is close to I. How close? Well, it's as close as I want it to be, right? To say that this is equal to something is really to say something about a limit. So that means that if I'm asserting that this is equal to I, it means that I can get the Riemann sum as close as I want to I by simply demanding that my partition is fine enough, regardless of how I exactly choose those sample points. And all of this talk about Riemann sums is reflected in the very notation that we've chosen for the integral. So here I've got the integral of f from a to b, and here I've got a Riemann sum, right? And this integral is defined to be a limit of these Riemann sums. And the notation really reflects their common origin, right? Here I've got a summation symbol, a Greek sigma, a Greek letter S, and here I've got a long S, right? Both of these are a kind of sum. And the thing I'm summing here is the function evaluated somewhere times a change in x, and the thing I'm summing here is the same thing. It's the function evaluated somewhere times a change in x. So I hope that even the way that we write down these integrals really reminds you that they're a limit of things that look like this, right? The function evaluated somewhere times some change in x being added up.